Bismillahirrahmanirrahim. Okay, so we saw double integration. We'll proceed on the double integration, and then we will see, the idea is that we'll see the triple integration. Triple integration. So double integration and triple integration. So that is the concept. So we will see. So we'll finish the double integration part, and then we will tackle the triple integration. I mean, anyone can go up to n number of integration if it has n number of independent components. So that is the idea. Now we are proceeding on the example where we have a semicircle. So we have a semicircle like this. Okay, so it is like we have a, okay, so we have a semicircle like this. So this is the place where we started the discussion, that with a semicircle. So this is a semicircle. If this is a semicircle, then we can consider that this is the arc, and this baseline is the bottom. If this is a semicircle, then I can place semicircle this in xy plane. If I place the semicircle in xy plane, so that is the concept. Okay, so if I place the semicircle in xy plane, and there is a z value, okay, so function over fxy. So function over fxy, so this is xy plane, and this is this is semicircle that is placed like this. Now function over fxy. So this is x-axis, and this is y-axis and x-axis. So function over fxy is y, in the sense that when it is x-axis, where x is, okay, where y is 0, along the x-axis y is 0, whereas here at the end y is the radius, that is 3. Here at the end x is 3, here other end x is minus 3. So here in between, that is the origin. So it is understandable now. This is semicircle, and in a semicircle this one is x and this one is y, then it is xy plane. Now it has radius 3, so here at along the x-axis y is 0, whereas parallel to x-axis y is 3, parallel to y-axis x is 3, parallel to y-axis this side x is minus 3. Now there is a fxy function over x and y, that is the z value. Z value is fxy equal to y. Y in a sense, when we are at y equal to 0, there is no height. So if this is xy plane where each point is x comma y, then there is a z value that is vertical to it, fxy. Now, if I proceed from here, then fxy is will go the way y goes. So y is increasing. So if this is xy plane, then this is x-axis and this is y-axis. So as we go, then y is increasing. Okay. Now here when y is increasing in this direction, z starts from 0 and it goes up. Okay, that is fxy equal to y. As y is increasing, then z value also increasing. Now I have to find the volume of the shape, whatever shape we are kind of drawing. So that is the concept. So as we saw that there are two ways of calculating the volume. One way is that we divide the xy plane into small rectangle, and in each rectangle we take fxy, one fxy. Either we average it around the rectangle or we take any value. It is up to us. So whatever is fxy is in that rectangle into dx into dy. So rectangle area into the fxy, that comes as rectangle into fxy, that comes as the volume of the rectangle. Now I have to add all the rectangles volume. That is approximation. Other is if I have a surface, if I have a surface like this, then I'll integration is nothing but calculating the area if I have taken 2D. So if I have one independent component and one dependent component, x and fx. So x is independent component, fxy is dependent component. Then if we are trying to calculate and there is a equation. So if this is x-axis, this is y-axis, and this is the equation of a line. If this is the equation of a line, then underneath the line, if I calculate the area, that is the addition. So if this line represents some kind of rate of change as per the independent component, then like rate of collection per hour or something like that. If I calculate the area, the net collection. So that is the concept of the integration as far as 2D is concerned. So in 3D, now in 3D where we have z equal to fxy, z is a function of fxy. If z is function over x and y, then this is 3D. So earlier we had one x independent component and one dependent component constitute 2D. Now we have two independent components, x and y, and dependent component is z, that is vertical to the xy plane. So it constitutes a volume. Now if I want to calculate the volume, then idea is volume is nothing but the area into height. Area is length into width into height. So now if we want to kind of calculate the area, then we can now see there are two kind of area. If this is xy plane, then and this is z, then this is xz plane. This is yz plane. Okay, so in approximation we had so many rectangles in xy plane, and against each rectangle that width and length is delta x delta y. The height is any point in the rectangle fxy. So fxy into delta x and delta y is the volume of that rectangle in the xy plane. Adding all the volumes, we get the net volume. Now here I have YZ plane. I have XZ plane. So XZ plane here, 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 here. At each separate Y, constant Y, we have separate XZ plane. So if I calculate XZ plane and multiply it by Y, then I get the volume. Or if I have YZ plane and multiply it by X, then I get the volume. So this is what we have discussed. So now the volume comes in fxy dx dy. So dx dy at any point xy, at in xy plane at any point xy, what is the fxy? That is the height into the fxy dx. If I say fxy dx, then it is nothing but we are computing the full-fledged integration where x is the independent component. Fxy dx where x is independent component. So we are calculating the area in xz plane. Whatever area we calculate, we again integrate in wider in xz plane. So along x-axis. So xz plane. Now this xz plane again we integrate with a dy. So whatever the area we receive, so against each y we have separate area. In y direction against each y we have separate area. Now we will integrate again this with the y-axis, and so the fxy dx, that is calculation of area in xz plane. Once we calculate it, whatever we get, then again we calculate in yz plane or multiply it by y, that is dy, then we get the complete volume. So that is the scenario. Okay, so we try doing fxy dy first. Fxy dy, so we can change it. So fxy dy dx or fxy dx dy both are same. So whatever the double integration we are making, we have to just shift it by shifting this. So we tried with, so now fxy is y, because if we have semicircle, then the z value increases as y increases. So y square by 2 is the integration. Now we limit it from 0 to 9 minus x square. This is what we saw. So limit what we put, that should be in function of x, that is required. First limit. Then whatever we calculated, then we again integrated with x, and limit we put minus 3 to 3. This is what? So if this is semicircle, then y limit is 0, 0 to 9 minus x square. 9 minus x square in the sense, if this is yz, this is yz plane, then yz plane when x is 0, this is x is 0 at the middle, then it is 9. 9 root 3 maximum. So if I calculate the y square by 2 and limit it 0 to square root 9 minus x square, it will come as 9 minus x square. That's it. Because y square by 2 will go away. 9 minus x square by 2. 9 minus x square by 2. That will be. So 9 minus x square is maximum when x is 0. So if it is yz plane we are calculating, then it is maximum when x is 0. Minimum when x is minus 3 or 3. So at this end, okay, at this end, if I see the semicircle, then at this end, in yz plane area is 0, at this plane y area is 0, while here the area is maximum when x equal to 0. So this is the one way we calculated, then we tried other way also. It was funny though. So y dx, and where it varies from minus square root 9 minus y square to square root 9 minus y square, minus square root 9 minus y square, square root 9 minus y square. And then, so we calculated the xz plane, in the xz plane. So this is in x, if I calculate xz plane, then this is maximum when y is 0, minimum when y is 3, like that. 9 minus y square, it is maximum when y is 0. So if I see xz plane, if I calculating dx first, then we are calculating the area in xz plane first. Whatever the area is, whatever area we are receiving, then that area we will multiply along the y. In first we calculated in yz plane, whatever came multiplied by x, means dx later we calculated. Now whatever comes in yz plane, in xz plane, that along the y. So x will kind of, it would, the limit what we will place is minus the square root 9 minus y square, 9 minus y square. Whatever it comes, then y will go from 0 to 3. So last integration will be constant. So here also we came, like if I do 9 minus y, if I y dx, then integration will come as yx. If it is yx, and from minus square root 9 minus y square to square root 9 minus y square, then it would come as 2y square root 9 minus y square. This is what we saw. Okay, then it would come as some constant 9 minus y square to the power 3 by 2. This is what we saw. Now we will integrate again y with dy, that will be 0 to 3, from 0 to 3. Okay, so first case we calculated it would come as 18. So in next case it should come as 18. Okay, so this is famous example in the double integration case. Now consider that this semicircle is city. This is a town. Okay, so this is a kind of city, and city is like this only. And city, whatever the base we are seeing, the base. So if city is like this, from base down it is ocean. So, or if city is like this, if city is like this, then the base from this it is ocean, and city is like this. If that is the case, then what is the average distance of the city from the ocean? That is the question. Actual example is like this. That if I have a semicircular city, and whatever we consider the flat area in the semicircle, beyond that it is ocean. So from every point, if I calculate the distance, so at any point that is x comma y. So if I take any point in the xy plane, if this is xy plane, then any point in the xy plane inside the semicircle if we take, that will come as x comma y. If that is x comma y, the distance of that point from the ocean is y. Okay. Now, if I want to calculate the average distance from the ocean, then knowingly, unknowingly, then this will come as z value. Y will come. So at each x point y, we have a value that is variable. At if there is a point called alpha beta, then distance is beta. If there is a point called AB, the distance is B. If there is a point called x, if there is a point called mn, then distance is n. So for any xy, distance is y. Okay, so any xy, if I put xy inside a function, then the whatever comes out is y. That is function over x comma y. Function comma over x comma y, fxy, means there are two independent variables. If I say Python code, then two variable will go inside the function x and y. What will come out is the function over x and y. So that is y. So fxy equal to y, z equal to y. So I have a function over fxy, xy, that is fxy equal to y. So if there is a function over x and y, that is z value. So it is knowingly, unknowingly, it is come as 3D problem. So surprising, right? Means if I have a semicircular city, and at the end of semicircular there is the ocean, then from each point in the city, if I take any point in the city, then there is a distance to the ocean. What is the average distance from city to the ocean? That is a simple question. So at any point in the city, if it is x and y, x comma y, then distance is y. So knowingly, unknowingly, we have a function over x comma y. So if I write a function where I push x comma y and try to take out what is the distance, it will return y. So function over x comma y is y. If that is the case, then we entered into 3D because for fxy is equal to z. So z equal to y. Now full area is in xy plane, then at each point we have y. So if it is near to the ocean, then y is 0. So z value would increase like this. If this is the city, if this is the city and this is the ocean, from ocean the y will grow like this along the city. So the volume what we calculate here is 18. This is what we calculated. If it is 18, then volume by area is the average height. So area is pi r square. That is area of a circle. It is semicircle. So pi r square by 2. So 18 by pi r square by 2. So 36 by pi r square. So r is 3. So 36 by pi 9. Okay, 36 by pi 9, where pi is 360 degree or 3.14, whatever comes handy. So 3.14 into 9. So 36 by 3.14 into 9. So it will come as around, okay, so 9 3 around 1.2 or something like that, or 1.1 point something, 1 2 or 2 something like that. So that is the average height. So average height starts from 0, it goes till y equal to 3, okay, in semicircular fashion. So how nicely we computed. Okay, I don't know 2D or 3D. I know basic algebra, that if I have a function over independent component, then it becomes a dependent component. Dependent component is orthogonal to both the independent components. So if independent component is x and y, since they are independent to each other also, then x, y will be orthogonal to each other. So they constitute a plane. Now, the dependent component on xy is z. So, I mean fxy. So, z is orthogonal to both of them. So, that is vertical to the xy plane. Now Z varies, and then we calculated the volume. So volume by area is the average height. So this is famous question and not related to any book. You can find anywhere that if there is a city that is semicircular, then what is the average height of the average distance of the city from the ocean? Okay. Now let's move toward 3D, 4D. Okay, so we calculated 3D. 3D sense that we have 2D means one independent component, one dependent component. That is 2D. So what all the story will happen in one surface. That is 2D. Now there is another guy called 3D where independent components are 3. I mean 2, x and y. If independent components are x and y, if independent components are x and y, then dependent component is z. If two independent components are there, then independent component itself they make a surface. And since dependent component has to be orthogonal to the independent component, then from surface it will be vertical. So surface and vertical it constitute 3D. So z equal to fxy is 3D. So we talked about 3D, 4D. 4D means now there are three independent variables x, y, and z. So there are three independent variables x, y, and z. So f, x, y, z. You can call it alpha. So alpha equal to f, x, y, z. So the 4D, how it will constitute planes that you can think of. Okay, so in 4D, now 4D independent component itself are 3D. So x, y, and z, no one is dependent upon anyone. X can take own value, y can take its own value, and z can take its own value. Based upon these three values, we have another dependent variable. Based upon these three independent variable, we have another dependent variable that is called alpha. Alpha equal to f x y z. F braces x comma y comma z. Fx y z equal to alpha. So alpha we can call, or we can call kind of okay, any name, any typical symbol in kind of Roman or something like that we can give. So alpha equal to fxy z. Let's solve this problem in 3D, in 4D also. So when it comes at 4D and there are three independent variables, then it will come as three integral. Earlier we had two integrations, one for x, one for y. Now there will be one for z because three independent components are there. So now it will be fx, yz, dx, dy, dz. So fx, yz, first we will integrate with either dx or dy or dz. So if I integrate with any of them, if I integrate it with dx, then the limit what we place, that will be the function over y and z. Then again if I integrate with the dy, then function would be in z. Then third will be constant. If I integrate with dz first, f x y z dz, then z limit will be in x and y. If I integrate x next, then x limit will be in y, and then y will be a y limit will be constant. So there are three integrations. First integration, second integration, third integration. Integration of fxyz, fxyz, function over xyz, independent component. Whatever the value we get, now we have to integrate separately dx, dy, dz. If I integrate with dz first, then the limit will be as a function of x and y. Then if I integrate with dy, then the limit will be as function of x. If I integrate with dx at the end, the limit will be constant. Okay, like in double integration, if I integrate with dy first, then limit will be in a function of x. Then if I integrate dx, then limit will be constant. So last limit will be constant, whereas the inner limit, first limit, if I move from right to left, the first limit or inner limit, the outer limit will be always constant. The first limit or inner limit will be function of whatever is the, it is the outside limits. So fx, y, z, dz will have limit because outers are x and y. So it will have limits in function of x, y. And then if it is dx, then it will be limit in the function of y. At the end, dy is there, it will be constant. So this is the scenario. Now let's try. So fxyz equal to y. So fxyz is not y. Means we expect that fxyz, the function, will have variable in z. Fxyz will have variable in z, but it is not in z. So better we will keep it 1. So 1 dz dx dy. 1. So we are integrating with the dz first. So when we are integrating with the dz first, then we will keep, since this fx y z is not in function of z, so we will keep it as 1 and limit what we place, it will be in function of x and y. So limit is, so if I see that the city is like this, then from here it is ocean. So z value grows like this. So it starts from 0 and it grows in y. So dz and limit is 0 to y. So at any distance y, so this is y, this is x, and this is z. So at any distance y, the z is y. So limit is 0 to y dz. So dz, if I integrate, it will come as z. Limiting 0 to y means y. So y, dy, dx, same story. Now, first integration, second integration, third integration, inner integration. Inner integration is 0 to y. Next is with the dy. So dy will be in function of x because outer is x. So that will be 0, 0 to square root 9 minus x square. Then outer will be minus 3 to 3. So the story is same. Okay, so we will proceed on this. So we will try with the kind of other other limits. So this limit we started with, this limit we started with dz. So triple integration we started with dz. Okay, then we'll try with dy first and then dx. So that's what we will. So d, okay, if I try with y first, okay, then what will be the fxyz scenario, and then we integrate with the y. So whatever the limit we make, the limit of the y should be in variation of x and z. So fxyz dy is the innermost, then fxyz I have to put something, and earlier we put 1, and then limit would be in the function of x and z. Next, if I keep it x, then limit will be in function of z. Then if I keep dz at the end, then limit will be constant. Okay, so we'll proceed with this example and we'll do the permutation combination with keeping one other, and we'll work on it, and we'll take more example in 3D. So oh, sorry, 4D. So where 4D means we have three independent components. Once we're done with this, then we'll have some brief introduction on kind of uh, a polar coordinate, okay, or radial coordinate rather, radial coordinate, cylinder coordinate, a spherical coordinate. But you will understand this only when you are done with the Cartesian coordinate. So 1D, we saw 2D, we saw 3D, now we are seeing 4D. And if we are thorough with that, then we can go for with radial, cylindrical, and spherical. coordinate system in the triple integration case, or I would say multivariable integration case. So as always, reiterating same thing, calculus is very easy when you understand step by step. Otherwise, miss, it's not possible. So let's move on.